This structural schematic abstracts a modern smartphone into three strict physical boundaries. Mobile hardware engineering has reached a plateau where the physical dimensions of the chassis and the chemical energy density of the internal lithium-ion battery have hit a hard volumetric cap. These devices rely entirely on passive cooling within a sealed chassis, meaning they cannot dissipate any additional heat. If the internal components generate more thermal load, the processor must throttle its output to prevent hardware damage. The leaked technical specifications for the upcoming iPhone 18 Pro architecture show how engineers are attempting to bypass these physical boundaries. The core dataset points to three specific architectural shifts: the transition to 2nm silicon fabrication, the adoption of LTPO Plus display backplanes, and the reintroduction of physical variable mechanical apertures in the primary camera. These specifications represent highly interdependent engineering solutions. Each shift is designed to steal fractions of a millimeter or milliwatts of power from one system to physically enable the next. Dissecting this specific architecture reveals the operating blueprint for high-density mobile systems. The primary optical shift in this device requires moving away from software-driven computational photography and returning to the absolute rules of optical physics. A variable aperture uses moving blades to mechanically control exact light transmission. This manipulates the depth of field before photons ever hit the sensor. A standard DSLR relies on deep physical volume for moving mechanics, but a smartphone restricts the optical z-axis under 10 millimeters. To fit this mechanical iris into that compressed stack, interlocking metallic blades must clear each other by fractions of a millimeter without failing. Hardware teams are taking on this massive geometric challenge because computational blur algorithms struggle to map complex textures like hair or transparent objects. A physical aperture provides authentic low-light photon management directly at the sensor level. It also provides true focal plane isolation. The optical physics naturally separate the subject from the background, providing a depth that code cannot perfectly simulate. Expanding the rear camera mechanics consumes interior volume. To offset this, the front-facing Face ID sensor array is being condensed into a smaller, reduced pill shape, salvaging critical real estate inside the display assembly. Forcing an electrical current to drive physical micromechanics, like snapping aperture blades open and shut, introduces a heavy, active kinetic drain on the battery. Introducing moving physical parts into a highly constrained solid-state device demands ruthless, offsetting energy cuts elsewhere in the system. Those required energy cuts begin on the main logic board with the transition to the A20 Pro processing architecture. Shrinking the gate length in the 2nm fabrication process drastically tightens the physical distance electrons must travel. Shortening this gate causes a steep drop in leakage current and switching energy. The processor does the same math, but generates far less heat. The system also integrates a new C2 modem and a dedicated N2 chip built strictly to handle Wi-Fi and Bluetooth arrays. The primary engineering value of these networking components lies in systemic power efficiency, specifically during high-frequency polling and sustained data loads. Maintaining wireless connections requires a constant polling of frequencies. Highly efficient modems heavily reduce the continuous electrical draw on the battery during these operations. Every milliwatt salvaged from the modem and logic board helps facilitate the device's expanded direct-to-satellite telemetry. Pinging a satellite in low Earth orbit from a tiny internal mobile antenna requires intense bursts of power. The cumulative energy saved by the 2nm node and auxiliary chips offsets the significant power consumption of the satellite antenna. This keeps the satellite hardware viable without exhausting the standard battery reserve during a transmission. In modern SoC architecture, shrinking transistors serves as a thermodynamic necessity to power new heavy-draw peripheral hardware. The final major power draw variable in the architecture is the display stack, driven by new LTPO Plus technology. This exploded view isolates the low-temperature polycrystalline oxide backplane, the gatekeeper for the pixels, that enables highly dynamic refresh rates. Throttling the refresh rate dynamically at the hardware level, dropping down to 1 Hz for static images, drastically cuts continuous power consumption. The LTPO Plus display and the 2nm node operate as a combined strategy to protect the fixed volume of the battery. The engineering philosophy of stripping away inefficiency also extends to the external ergonomic interface, specifically the side-mounted camera control. This blueprint sketch details the removal of the complex capacitive and haptic slider, replaced by a traditional tactile mechanical button. Replacing an advanced multi-touch sensor with a basic click mechanism is a technical simplification that results in a major progression in practical industrial design. Physical mechanical reliability supersedes theoretical interface complexity under unpredictable field conditions, like moisture or gloved hands. This tactile focus carries over to the chassis materials, with a shift to a frosted glass backplate. Altering the surface material texture directly influences the perceived thermal and tactile density of the unit. Engineering mastery requires the discipline to strip away inconsistent sensors in favor of reliable physical mechanics. This 3D wireframe maps a unified systemic response to absolute geometric and thermal constraints. The efficiency of the 2nm node and the LTPO Plus display preserve the strict energy budget required to actuate the kinetic aperture and the satellite arrays. Packing these interdependent micromechanics into a static 10mm form factor carries a steep economic consequence. Achieving this level of component density demands extreme precision tolerances across the global supply chain, from the silicon foundries to the final glass assembly. As hardware engineers push thermal and spatial architecture closer to their absolute physical limits, base manufacturing costs inherently rise. This architecture represents a systemic orchestration of physics, forcing separate optical and silicon systems to function within a singular, rigid thermal envelope.